We are the cooktop alarm group, or the compact stove cooktop alarm device. My name is Reardon McCall. I'm the team lead. This is Jared Trottier, and this is Matthew Sherman. And our advisor is Dartmouth, and our sponsor is Granata. So our project is pretty straightforward concept and idea. It basically is a device that any consumer can deploy on their stove, and it basically monitors the stovetop for heat dissipation and a active user in front of it. What is this used for? It's basically a device that we need for those who forget to turn off their stove when they walk away, or anyone that is constantly maybe cooking in front of it and then stepping away for a long period of time, going to a different room, and forgetting about it, and ruining possible with that. It is specifically supposed to be low power and a low cost device, so it can be easily marketed to consumers, and we believe that we were able to accomplish that.
So these are the customer requirements that we had, that we set up previously with our customer back in September and October. They basically have not changed since then, and we turned those into the engineering requirements, tacking numbers on top that you see in the following slides. The key points here are the device needed to be able to detect a lit and unattended stove. So to do that, we had to be able to interface with a sensor that can detect heat, 4 of them to be specific, and a motion sensor as well. On top of that, we needed the device to be small, easily deployable with minimal user interaction, so no wires, anything of that nature. So our device had to be battery run, and being that it's supposed to have minimal interaction and it's supposed to act as sort of a public safety device, we should also have a relatively lengthy lifespan on a single set of batteries. And on top of that, because it's supposed to be built with the intention of mass production, we wanted the individual units to be relatively cheap at around $30, and specifically for how it functions, we needed 4 infrared sensors to detect if the stove is on and if users pass in front of the motion sensor, or aka they are actively in front of the stove, the system clock should effectively reset itself, and otherwise it should set off a loud, audible beep.
Here are some constraints and standards that we apply to our project. The constraints are pretty straightforward, most of them being the nature of the pieces that we use and the device size and shape, and making sure that we stayed economical when it came to populate the PCB. Lead time for parts and as well as the accuracy of the test equipment that we used was also taken into consideration. Some standards we discovered in the National Electrical Code, or the FPA 70. We also suggest to our customer to look into those standards, as well as we follow the IEEE Code of Ethics throughout the process.
So we went through a few different alternatives while going through the different hardware that we could use to build our device, the first of which was a CPU. So specifically, one of our customer recommendations was he wanted us to use a M0 ARM processor, and along with that, he also wanted a longer battery life. So early on, we had recommended to him the use of a Atmel 328P instead of a SAMD21G, and that was because not only did we have previous experience using this component, but we also knew that it had an average lower operating power consumption, at which point it would generally have a slightly better time of achieving that longer lifespan. But in every other way, compared to a SAMD21G, it was effectively the same, so we just decided to stick with the SAMD21G to abide by the customer's recommendation?
So the a big part of the project is the fact that the device has to sense temperature. And so to do that, we started with a photodiode circuit, an MTD photodiode. And it wasn't sensing enough to differentiate between small increments of temperature, and it would only notice the heat when it was intense, when it was an open flame. So we moved to a thermopile instead, a ZTP series thermopile, which sees a much higher range of infrared waves and allows the device to work efficiently. And there's the op-amp. The op-amp takes the signal, the op-amp part of the circuit takes the signal given from the thermopile. The thermopile only gets a small voltage signal. So the op-amp circuit amplifies the signal from the thermopile to, and we chose the TLV op-amp, which was picked for the requirements and the engineering requirements, and used all the way through most of the project. There was a little bit of an issue with it, but it works for our project. We do suggest that if a customer would like to expand the battery length and the lifespan of battery, to use an op-amp that requires a lower supply voltage. For that, we suggest an OPA op-amp, which goes the TLV op-amp goes within a range of 2.7 volts to 6 volts, and the OPA op-amp goes from 1.8 volts to 5.5 volts. The software actually allows the op-amp to work for the 3 months that we expect the device to go without needing new batteries through sleep mode feature.
So our actual device consists of about 4 subsystems. Those 4 being one being the motion sensor, the device that actually detects the user that is actively in front of the stovetop. The second subsystem would be the alarm, or the actual device you hear when it goes off. And the next subsystem would be the 4 temperature sensors that are on the actual device that sense the conventional 4 burner stovetop or conventional stovetop. The next one is the power supply and LED and software system. Those are all combined into one because they all interact together consistently enough to be a subsystem of their own. So our project consists of, like I said, the subsystems. They can kind of broken up into modules themselves. As you can see right here, this is the motion module, and this is the actual daughter board that that you can actually break out from the actual main board, which is right here. And that houses the actual CPU, battery, and LED that will interface with the actual module with the motion. And the temperature sensors over here on the right, we have 2 different ones because the way that we had to lay out the board. They're essentially the same device, just mirrored on top of their pins, so you can actually just move them around a little bit easier. So this is our technical design, and this is the schematic that we actually did in Eagle right here. And this is larger. You guys really can't tell because it's kind of not the best lighting. But this is the actual CPU, and this is where the temperature sensors are right here, and this is the motion sensor, and this is the op-amp circuit with the 4-watt op-amps inside it, integrated circuit. And this is basically what we use to make our PCB layout, which we ordered through Oshpark, and it turned out pretty well actually. It works totally as we expected, and it's very efficient in terms of the way the actual modules come to us, because all 4 of the temperature sensor modules are on breakout boards, so we only need to order 1 per system that you want to make, in addition to some motion sensor monitoring you also have to order. So it decreases the price basically by a lot to order.
So the way the software was developed, it effectively cuts the system in half a couple of times. The first half being if the system detects that the stove is above the threshold temperature, which we currently have set at about 130 degrees Fahrenheit, or below it. If it's below it, the device continues to operate in a sleep mode to minimize power consumption, and it continues just pulling over time to see if it ever goes above the threshold. And if and when it goes above the threshold, it switches all of the components on, and it starts pulling much more actively. And from there, the system is then divided into if the temperature is staying the same or growing, or if the temperature is decreasing. If the temperature is decreasing, then the internal timer that we have set continues decreasing over time, but nothing else happens, and it just continues pulling. However, if the temperature is staying the same or increasing, the timer continues ticking down, and it also references the motion sensor. If there has been motion in a certain window, then the timer fully resets. Otherwise, the assumption is that the user has forgotten or simply just not attended their active stovetop, and the stovetop is in fact active, at which point the device sounds an alarm. And from there, if the temperature is decreasing, then if it ever decreases below the threshold value, the clock also resets and the device goes back into a sleep mode, and the cycle continues.
So this is our verification cross-reference matrix that we use to determine what tests and what type of tests we'll be doing for each individual engineering requirement, whether or not we're doing a test, demonstration, interpretation, or sorry, inspection or analysis. We basically paired what we thought was best to each requirement and proceeded that way from the beginning and how to assess each issue that we had. This is our second set of the VCRM to house the actual engineering requirements to the verification. So our tests went really well, but most of them that we set up passed the way that we set them up, kind of straightforward. We would deploy each subsystem in a way that would allow the tests to specifically address the subsystem. And overall, they worked well. They gave us the results that we needed. And then we created a test at the end to actually test the whole entirety of the system. We're specifically going to talk about a couple of tests that we feel were necessary and explain.
This is the temperature sensor test case. To test the thermal pile, we use analog discovery to get a voltage signal that translates to a digital value used by the software. From the photodiode to the thermal pile, the circuit became slightly more complex, as the thermal pile includes a thermistor to monitor and compare the local temperature with the direct temperature that the thermal pile is sensing.
So this is a relatively straightforward test. As previously stated, one of our requirements by the customer was that he wanted to be capable of mass producing this product for consumer use to be able to sell. So we approached a parts list of everything that we used to develop this board from the guise of ordering in bulk. We, for the purposes of this demonstration, chose a quantity of 1,000. And from that perspective of buying in 1,000 bulk, we were able to get a unit price for each individual fully built module of $26.14, which is a little under $4 below the initial desired cost. As well, after that, this is just a picture to depict everything that we used to prove the full system functionality. We used a hot plate, as you actually see in front of the room, along with a temperature sensor and an oscilloscope, the analog discovery, to prove the system's function as we move the device around. That'll be shown in a demonstration video later on. But For the purposes of test case, this allowed us to prove that input was being had from motion, input was being had from the temperature sensors, and after a certain amount of time when there wasn't motion, the buzzer would also sound.
As for every other group, we had a plan and schedule initially set, and we followed it to the best of our ability, but of course, some cases, we fell behind. Theme of the day. So each group has to abide by the test plans, the CDR, the final presentation, and what we're doing today is our actual presentation and report. But we also had to do we had to send out our PCB and order parts as well. And this is the actual case of which we fell to for some of those more important aspects, like ordering the PCB, which we thought would take a certain amount of time, but ended up taking quite a bit longer. We had an initial design from last semester, but when we were modifying it, it took a lot longer than we expected. It actually took a lot of hours. In addition to that, finalizing our prototype and integrating that was delayed due to getting our PCB in late. So for the future, starting that early would be better for the day. So like I was saying, for future work recommendations, starting a little bit early and getting that PCB out earlier, but also creating an enclosure. We wanted to create an enclosure for our device, maybe a 3D printed model, and get it actually on the device and cover it to kind of present the final product. But instead, we are leaving the circuitry open for everyone to see. So future work would be to create an actual enclosure, get that printed out, and potentially present it to our customer as a design that we think would eventually be good for housing and casing. We also wish we could have done longevity testing for our actual system, since our device is supposed to be for 3 to 4 months as a kind of a safety device. We wish we could have deployed it and let it kind of run on its own for a long period of time, but we don't have that time, obviously, with the semester coming to an end. We also wish we could have tested out a couple more components, specifically a couple different op amps, as we see that some of our op amps could have given us a longer life if we chose a different one. And also a motion sensor, because ours is very sensitive to motion, and we wish we could have tested a couple more just in case, even though it is functional, we wish we could have done that.
Here are some lessons we learned and a quick summary. Time management, of course, everyone has said pretty much the same thing, that we have a certain amount of time and a lot of stuff to do in a very short amount of time. And also group work. It's important to be able to communicate with the group, work within the group, and I think we're pretty lucky we all work off each other's strengths really well. And overall, just, yeah, it's teamwork and time. That's really what it is. So the stovetop alarm device began as an idea from Chris Granata, and we hope that we have made a reality, to borrow a cliche. And though we had to change a few things along the way, we think we believe we have a functional, effective result, and we're pretty proud of it.
So this is our demonstration video to test all 4 of the actual sensors on it. You'll see that every time we move the device, we do turn it to show that functionality of the device. We set the timer for the actual device to be really low, because we're not going to wait 5 minutes, which is our current threshold for sensing a user and resetting the timer. So we set that threshold really low for this demonstration purpose. As you can see, it's going off. It senses the hot stove. We moved it. We're rotating the actual device. Check the temperature. Goes off. Reset the motion. Turn the actual device to test the other module. Check the temperature to ensure that it is above 165 degrees Celsius or 155 degrees Fahrenheit, roughly around that. Goes off. Reset the motion. Rotate the device. Check the temperature. And the device goes off. So that is conventionally the idea that that would work on a 4-burner stovetop if we had 4 burners around it. Specifically for the device, in this test, we wanted to show that it does work, and we also had to isolate no motion because we had to be right by the camera. We would just like to acknowledge a couple people for our actual project. Dr. Karen Payton for our advisor, for giving us a lot of advising support and technical information about the project. Chris Granata for project funding and management. Dr. Ben Vile for his expertise in microcontrollers and PCB design. And Dr. David Rancourt for his expertise on circuitry and analysis of op amps. And Dr. Vance McCullough for invaluable real work lessons and advice. And the whole refrigerated door alarm group for collaboration on group work because our projects are similar enough. Questions?